now going to study a few parts of Chapter 4, and if you've taken discrete mathematics, these two parts should look very familiar to you. Section 4.1, which is this video, will cover the well ordering principle, which is essentially proof by mathematical induction, and then we will look further in our next video over recursive definitions. So mathematical induction is just a method of proof, and in discrete mathematics we talked about several different methods. We will continue those methods in this course. So this is just a reminder of what mathematical induction is all about. Essentially what we're saying is if we can prove that some statement is true for some least element, which we'll get into more in just a little bit, and we can prove that whenever s of k is true, which means this statement is true for some value, then it's true for the next value, and again we're dealing with integers, positive integers, then we can say that it's true for all. So we're saying if we can prove some starting point, and we can prove that wherever we are, we're able to get to the next element, then we can prove it's true for all of the elements in the set. So again, a good visualization is if we have a ladder, and the first one, which we call the basis step, is saying I can get to the first rung of the ladder. The second step, which is called the inductive step, is going to say if I can get to any rung of the ladder, then I can get to the next rung of the ladder. Which means, let's say this is the rung, well then I can get to the next one. Well, if I can get to this one, then I can get to the next one. If I can get to this one, I can get to the next one. You get the idea. It's basically showing as long as I can get here, and for every step that I get to, I can get to the next step, then for sure it's true I can climb to the top of the ladder. So before we get too involved in actually proving anything by mathematical induction, we need to talk about the well ordering principle and what it tells us and why it's important with mathematical induction. We also need to talk about the fact that dealing with positive integers is pretty important. So here's why. Positive integers are integers, of course, that are positive. So positive whole numbers, essentially, which are sometimes called the counting numbers or the set of natural numbers, 1, 2, 3, etc. So let's suppose I have a set of values that all of the values in the set belong to the integers, the positive integers, that it's not the empty set, meaning it actually has at least one element, and that s is bounded below. So I'm going to make up an example. Let's say 1, 2, 3, 4. This set that I've just made up fits the description. All of my values are positive integers. It's not empty. S is bounded below. In this case, it's bounded below by 0. And 0 is not a natural number, but what I can say is that 0 is a bound, which means if I'm dealing with positive integers, I'm never going to have a value that is below 0. So that is a bound, even though it's not part of the set. The well ordering principle says that because all of those things are true, because we have a countable set of things, it's not empty, it's bounded below, that there's going to be some value that is a least element. And that least element will be the one whose value is below all of the other values. So in my case, that would be 1. So why am I making such a big deal about z plus, or the positive integers or non-negative integers? Well, let's see what happens if I try to replace it with q plus. So q plus means a rational number. Keep in mind that the definition of a rational number is essentially some value that can be written as p over q, where both p and q are integers. So essentially we're saying I can write it as a fraction. Does my set of non-negative rationals have a least element? No, in fact, it doesn't. Here's why. This is another method of proof by contradiction. Let's say I've got some value x that I'm saying is the smallest positive rational number. So again, according to my definition, which I've essentially recopied here, I'm saying x is greater than 0 because it's positive, And x can be written as p over q, where p and q are both integers. Definition of a rational number. However, let's say I take x and I divide it by 2, which means I'm taking half of x. Well, half of x would be equivalent to p over 2q. But since q was an integer and p was an integer, and I'm just taking 2 times q, that's also going to be an integer. So essentially I'm dividing an integer by an integer, and that's going to be a rational number. Therefore, x divided by 2 is a rational number, but x divided by 2 is less than x, and therefore x was not my least value because I just divided it in half and found another least value. So you can see that by contradiction, it is not possible to have a smallest positive rational number. So why do I care? Well, because I can say that z star has a least element because that least element will be 1, or whichever value is, greater than that in the integers. However, I can't rewrite q, which is rationals, or r, which is real numbers. I can't do either of those in this second method where I'm saying that it's or equal to something. Now, does it matter? Yes, because we need to be using those positive integers in order to use mathematical induction, because mathematical induction relies on the fact that there is a least value and that it's bounded below. So now that we've talked about the well-ordering principle, let's get back to induction. S of n is going to be some statement that involves one or more occurrences of the variable n, which represents a positive integer. So n is some positive integer. So if the statement is true for 1, and if whenever I can get to s of k, which is true for some particular but arbitrarily chosen k that is an integer, then the next value is true. S of k plus 1 is true. And if that's true, again, then S of n is true for all of the values of n that are positive integers. So this is really, we've already talked about this is essentially the definition of mathematical induction. It will make more sense once we actually prove something through mathematical induction. Before we do one example, our first example together, just keep in mind that the basis step does not necessarily need to be that S of 1 is true. So S of 1 just represents that it's our least element. So our least element could be 5 or 100 or 1,000 or negative 22. It still works if we're looking at the lowest element in the set and then the next consecutive integer. So let's just call that least integer n sub 0. So essentially what we're saying is, assuming all values are integers, so not rational, we can say if a statement is true for the least element, and if we can prove it true for s of k, then it's true for s of k plus 1, then it is true for all of the values that are greater than or equal to our least element n sub 0. Now, I'm going to go through some examples with you, and I tried to not use the examples from section 4.1 of your text. I would definitely suggest looking over those examples as well. Mathematical induction isn't so bad once you get used to it, but if you haven't had discrete in a while, you don't remember it, etc., good idea to go back and look at your notes from discrete and to look at the examples from 4.1. So let's take a look at this first example together. You'll see that I have taken this out of your textbook, page 208, question 1, part A. It says, prove that it's true that if I take 1 squared plus 3 squared plus 5 squared, which is essentially odd values squared, up to my last odd value, that if I add all of those up, the summation is actually equal to n times 2n minus 1 times 2n plus 1, all divided by 3. And notice it's telling me for all of the n's greater than or equal to 1. So my first step is that I have to define what is S of n. S of n being, what's the statement that I'm trying to prove is true? Well, that's pretty straightforward. They've already told me what they want me to prove is true. That's my S of n. Step 2 is I need to show S of 1 is true. Now when I say S of 1, I mean the lowest element. So in this case, because n is greater than or equal to 1, 1 is my lowest element. So I'm going to use this pattern and say S of 1 would be that 1 squared is equal to 1 times 2 times 1 minus 1 times 2 times 1 plus 1, all divided by 3. That gives me 1 on the left-hand side. That gives me 1 on the right-hand side. That's true. Good. Step 3 says assume S of k is true. Prove that S of k plus 1 is true. So what I'm going to do is not super tricky. I'm going to take everything that this says and I'm going to replace n with k. And I'm going to say that's true. Then I'm going to say, okay, what if I added the next element? So what's the next element? So before I uncover that, let's take a look. If I were going to add the next element, if you'll notice, it looks like there's an increase of 2 each time. So my next element here would be 2 more than that, essentially, which would be 2n plus 1 would be 2 more than 2n minus 1. So this is going to be what I'm going to add to the left-hand side. And that means that I need to prove that that's true for, and again, because I'm doing step 3, this is actually going to be a k. But then that means I'm going to take, instead of n, it's k. I'm going to add 1 to that. And then 2n minus 1 means I'm actually adding 1 to the k, which is n, which gives me 2k plus 1, because I'm actually adding 2, because k is being multiplied by 2. And then this one's going to be 2k plus 3, all divided by 3. So I point that out because I just kind of jumped straight to it here, and I wanted you to see where it came from. I already know that this is true, that this part is equal to this, if I replace it with a k. So notice that's going to be my first step. I'm going to assume that this guy is true, S of k. So notice all I did was take the exact same thing I had here and replace it with k. Then what I'm going to do is I'm going to add this to each side. So that's what I've done. I've added 2k plus 1 quantity squared to each side because I have to add the same thing to each side. My goal then is to show that once I do the math on this side, that it's going to look like this. That's my goal. So let's take a look at the math that leads up to that. On the left side, I have exactly what I need. So if you'll notice, I'm not changing anything on the left side. I'm looking only at the right side of the equation, which is this guy. Let's continue to reduce that. So if I took 2k plus 1 quantity squared and I wanted to write it with what I already have, notice I'm just going to take it times 3 and divide it by 3 because this guy already has a denominator of 3. That way I can kind of combine those things together. Deal? So now I'm saying, well, let's try to simplify what I can. And it looks like I have a common factor of 2k plus 1 and a denominator of 3. So I factored that out. That left me with k times 2k minus 1 plus 3 times 2k plus 1, because remember we only took one of those away. Then I just multiplied that out, kept this guy on the outside, did the math in here, did more math in here, hey, did more math in here, and then said, hey, look, I can write that all as a fraction. And look at what happened. I ended up with exactly what I said I wanted to end up with. So because S of k implies S of k plus 1, then it's true for all, so that should be step 4. Because I proved that's true, then we state that S of n is true for all n that is a positive integer. That's essentially the 4 steps that you're going to go through. Now I realize I haven't done a lot of practice with you yet, but I'm giving you another practice that is very similar to the practice that we just did so that you're getting used to it. So I really would like you to try this one on your own first. Again, you'll want to pause it. I'm not going to sit here with just an open mic while you work it out, so make sure you press pause. Try this question. When you're done, press play to see how you did. So again, the first thing I'm going to do is define that S of n is the statement that I'm trying to prove is true. Then I'm going to show that it's true for 1. So again, this one in this case would be that 1 is equal to 1 squared. Well, that's true because 1 is equal to 1. So easy peasy. And again, I used 1 because it says for all of the n's greater than or equal to 1. So 1 is my lowest element, least element. Then I need to prove, assuming that it's true for S of k, which is essentially me taking S of n statement and replacing n with k, I need to show that if I take the next element and add it to each side, then it will end up as k plus 1 quantity squared. That's what I'm trying to get to. That's my end goal. Why is it my end goal? Because I'm saying this is true if I add the same thing to each side. Would I then end up with k plus 1 quantity squared? So let's take a look. S of k plus 1 would be all of the same stuff I had before, and then adding k plus 1. So using this formula or format, that would be 2 times k plus 1 minus 1. And notice, I've just added that to each side of the equation. And again, the left-hand side is exactly what I want. So I'm not going to do anything more to the left-hand side. The right-hand side, I'm trying to get to here. So to get to here, let's take a look at all of this and simplifying. I have the k squared that I had out front. I have 2k plus 2 minus 1. I'm combining like terms. The plus 2 and minus 1 gives me plus 1. The other ones I just rewrote. That happens to factor into k plus 1 quantity squared, and voila, that is exactly what I wanted. So again, and don't forget step 4. A lot of people end right here and they say, okay, good to go. It's okay at the end to say, hey, look what I just did. I just showed that because S of k implies S of k plus 1 is true, then the results follow for all of the n's in the integers. So let's look at a different kind. Still mathematical induction proof, but now I'm proving a summation formula. And it's not one of our normal summation formulas that we use very often, but that doesn't make it any less valid. We are trying to prove that this, in fact, is true all of the time. So I'm going to start step 1 by saying, let's say this is S of n. That's what I'm trying to prove is true. Step 2 is going to be for S of 1. S of 1 says replace n with 1, which says 1 over 1 times 1 plus 1. So I don't have to add anything to that because there's only one value. Does it equal 1 over 1 plus 1? Well, I get 1 over 2 on the left, and I get 1 over 2 on the right, and those are equal, so it's true. Step 3 is that I have to say that S of k is true. And notice I'm just saying all of this except with k's instead of n's. And then I'm saying show that because S of k is true, and then I'm going to manipulate that, I need to show that k plus 1 would be true, which means I'm going to 1 further on the summation, and I'm going to 1 further here, and I'm going to 1 further here, which ends up being k plus 1 over k plus 2. So this should be where I end up. That's my goal. And it's not a bad idea to say it. I always say it. Because this is true, I need to show that this is true. So I know that when I get to that point, I am done. So how am I going to do this? I'm going to say, okay, well, let's take a look at what this guy would be. This guy being going all the way to k plus 1. Well, I already know that if I go to k, then it's this. Then it's essentially me saying I want to go one more than that. So if I went to the next one, it would be 1 over k plus 1, k plus 2, according to this formula, which I've already said is true because that's s of k. Now I just need to do some math, right? I need to get to the point where I can simplify. Well, I know that this guy is equal to k over k plus 1. And I know that because I said assume that this is true. So notice that's all I did on my next step is I replaced that with k over k plus 1. I left the other guy by itself. Then I said, all right, well, I want to write this as one fraction. So let's take this guy times k plus 2 and times k plus 2. Because then I can have a common denominator. Well, that gives me k squared plus 2k plus 1 over k plus 1, k plus 2. I did some factorization on my numerator. Turns out k plus 1 reduces. And so here's my final solution. Is that where I wanted to end up? It sure is. So again, that was step 3. Step 4 says, hey, look, I did it. Because I showed that assuming k plus 1 is true, it tells me that assuming s of k is true, then s of k plus 1 is true. Then it follows for all n that belongs to z plus or all of the positive integers. Therefore, it's true for all of the n's. Again, here's a summation formula for you to try. This is one of the formulas that we use all of the time. It's one of the commonly used summation formulas that says the summation from 1 to n of I is equal to n times n plus 1 divided by 2. So you might remember it from calculus. You might remember using it in discrete. Essentially what I want to do is prove it, again, using mathematical induction. Obviously this is an example in your text, so you could just cheat and look in your text, but I'd ask you to actually try this on your own first. When you're ready, press play to see how you did. So again, it looks like I skipped the step that says S of n is this, but again, that would be my step. S of n is this statement. Then I would say S of 1 is true, so I would plug in 1 and make sure that it is in fact true, which of course it is. Step 3 is to say because S of k is true, then S of k plus 1 is true, which would be this statement. Instead of going to k, we're going to k plus 1. Instead of k times k plus 1, it's k plus 1, k plus 2. So now what am I going to do? I'm going to take what I know to be true and add k plus 1. And then what I know to be true and add k plus 1. And then it's just math from here. So this stayed the same. This guy I wrote with a 2 because I want a common denominator so I can combine them together. So by doing that, I got 2 is my denominator and k plus 1, k plus 2 as my numerator. And that's where I wanted to end up. That's what I wanted to show, and I did. So because I was able to do that, using mathematical induction, S of n is true for all of the n's that are integers. Here's one more for you to try, and I haven't done one of these with you, so it's really just a challenge question, and then I'll go over it with you. This is page 208, number 4. A wheel of fortune has the integers from 1 to 25 placed on it in a random order. Show that regardless of how the numbers are arranged on the wheel, there are 3 adjacent numbers whose sum is at least 39. So let's take a look. Again, if you feel up to it, press pause, try this question on your own. If not, let's go through it together. So we're going to say x1, x2, etc. all the way to 25 denote the numbers in their order on the wheel. So not that x1 is equal to 1 and x2 is equal to 2. We're just saying those numbers are the numbers on the wheel. We're going to assume that x1, x2, x3, which are the first three numbers on the wheel, are less than 39. That 2, 3, and 4 are less than 39, that etc., etc., etc. Any three that are next to each other are less than 39. With me? So essentially I'm saying it's not true. Since each of the terms appears exactly 3 times in all of the inequalities that I would have written, obviously I used the ... because I wasn't going to list them all out, but each term appears 3 times, then each of the numbers from 1 to 25 occur 3 times, because those x1s, x2s represent whatever those numbers are. So then I can say, essentially, that I'm rewriting it. The summation from 1 to 25 of 3 xi is less than 25 times 39. Where did I get that? So, by the way, this is not a proof by mathematical induction. This is a summation formula. I think you probably got that. Where did 25 times 39 come from? Well, I'm saying that each of these is less than 39, and there's 25 total sums. Therefore, the total sum has to be less than 25 by 39. But the summation from 1 to 25 of 3xi is, again, let's move the 3 out front, so 1 to 25 of xi. Well, we just said a moment ago that if we have the numbers from 1 to n, that it's n times n plus 1 over 2. Well, that's 25 times 26 divided by 2 times 3, which is essentially 39 times 25, but that means we have a contradiction. So because we have a contradiction, then our initial statement that all of these guys are all less than 39 must have been false. Therefore, there must be at least one occurrence where 3 adjacent numbers, the sum is at least 39. This is just a reminder of the summation formulas that we use quite often. So we just a few moments ago proved this is true, and then in our Wheel of Fortune example we actually used that for a proof by contradiction. But the rest of them can all be proved as well. I'm not going to ask you to prove them necessarily. Most of the proofs you can just find if you Google. I don't remember if I gave you one on homework or not, but you get the idea that these can all be proved by induction, and these are all summation formulas that you should hopefully have committed to your memory through calculus or discrete or in this course.